is a stochastic process or random process, and WT is also a random process. WT is a specific random process, call it Euler process, that follows certain properties that we went through. Now, if you solve this stochastic differential equation using E2 calculus, you will end up with this equation. So where ST is basically, you can plot it. You can plot ST. This is T, and this is the stock price, ST, and you will see that if this is the starting price, S0 is the starting price, and then you will see that it's going to look like this. It's going to look like that, and you will have this confidence interval or boundary plus minus 1 standard deviation that I will have in the assignment. Okay, so it will look like this if you plot carefully. Now, how to come up with estimating mu and sigma from historical closing price? Given historical daily closing price, so I'm going to open this data. Let's say this column, I think this is high, low, this is daily closing price. So you focus on this column. These are daily closing price, 149.46, 148.85, and so on. So I denoted this daily closing price with S0, S1, daily closing price, S0, S1, dotted, Sn, where N is basically for 5 years, we have 5 times 252. 252 trading days, so therefore total number of days. So you have this many closing price data. The parameters mu and sigma for modeling stock price, dynamics under geometric Brownian motion can be estimated. We are interested in mu and sigma. How we do that? So we assume that let us assume SI and SI minus 1 are daily closing prices of a stock on I and I minus 1 day. So let's pick 2 days of closing price, and then from these 2 days closing price, what you do, you find the daily log return. People who actually analyze this stock market, they use this parameter a lot. Log return. So logarithmic return means you take natural logarithm of these two stock price, SI and SI minus 1. So you take natural logarithm and you get this RI. So for I equals 1 to 5 times 252, number of days that you are working on. So you have that, this RI. Now the estimated sample mean or average daily return, mu hat daily, and standard deviation daily volatility of returns are given by this formula. So now you have mu daily and sigma daily. So you use this formula to find the estimated daily return and estimated daily volatility. Now you just multiply them with 252 to get yearly return. So this is your yearly average return, and this is yearly average volatility. yearly average volatility. Okay. So this, as I mentioned, like this 252 represents the approximate number of trading days in a year. Therefore, the calibrated geometric motion, you now, once you have this mu and sigma, the calibrated geometric Brownian motion model is given by this equation. Now you now have mu, sigma. Now use E2 calculus to solve, and the solution of this differential equation is given by you. You guys understood? It's pretty straightforward. I gave like it requires entire semester basically. So go through all these E2 calculus and all the background. So I summarized it in 3 pages. So that's all the background you need for the computer assignment that I just posted. Now we will move on to another topic called Kalman filter. Now that Kalman filter is coming from the idea of this stochastic, of this geometric Brownian motion. Guys, as I just mentioned, do you see this volatility? This volatility is increasing as you increase time. Okay. You know the stock price today. So tomorrow, given the world condition, maybe you may predict tomorrow's stock price. Now, look at the uncertainty. Uncertainty of you predicting tomorrow's stock price is going to be significantly less than the uncertainty that you will predict the stock price in 5 years. Yes or no? It's natural, right? Like uncertainty in 5 years is going to be significantly higher. So that's why I did, when I plotted, and you will actually see practically, that you will see once you solve this geometric Brownian motion equation or stochastic, the E2 differential equation for stock price, you will see that this fluctuation will be higher and higher as time goes. Okay? Now you don't want this fluctuation, this prediction. You want this prediction to be smaller. You want the uncertainty of this prediction to be smaller as time passes. Okay, that's what you want, right? So it's natural that we want our prediction to be as accurate as possible. And how you do that? So for that, again, this requires complex analysis, but we are going to start with a simple theory that actually starts from linear system. And it is first invented by Kalman, scientist Kalman, who was MIT professor who actually died in 2016, right after I came at graduate. So he died actually. And I did use many of his books. I did use his theory, extended Kalman filter. Actually, my entire PhD work is based on his theory. Okay? So his theory is extremely useful. Like people these days, self-driving car, like a lot of navigation problem, cannot go anywhere without his theory. And it actually came after his name, called Kalman filter, and we are going to go through that. And if you simply Google, you will see it's quite well established. Kalman filter. Yeah, that's basically well established theory right here. So there are some theory, there are some advanced version of this Kalman filter, for example, unscented Kalman filter. Unscented, scent came from the unscented Kalman filters, because this Kalman filter has some limitation, because it works with linear system, and also it works with noise that is modeled by Gaussian. But in reality, in practical situation, noise is not always Gaussian. So that is one limitation, and people did extend his theory. And like the original version of his theory remained the same, but people did extend it many different ways to solve complex problems. And today, what I am going to do, I am going to start with a simple problem on one-dimensional vehicle. One-dimensional vehicle. Does it look like Tesla's Cybertruck? I drew this using LaTeX. All programming. It's a piece of code. It's not. I did not use any graphical thing. All programming. So I'm going to make it look like this. So I will update this figure. But the main idea here, I'm not going to go through. I did explain what's. What is linear time invariance? Actually, Dr. Lu go through linear LTI system, linear time invariant system.
Yeah.
Right? Yeah. So LTI, linear time invariant system. That's Dr. Lu. It's in 302, in 301. You did go through linear time invariant system, and linear time invariant system. I just for you to brush up the linear time invariant system that it follows the superposition principle. So a system is said to be linear time invariant if it follows superposition principle. So I summarized it right here, and then I moved on to direct application of LTI system. So here, let me talk about the system itself. So I considered a one-dimensional vehicle. The vehicle has mass m in kilogram. If I do not mention anything, make sure that you use the unit SI unit. And the vehicle accepts this UT is basically the gas that we apply. Okay, I model this UT as the force which is time varying as a function of it is time varying, and this force unit is, what is the unit of force, guys? Newton. So it is N. Okay. Now this vehicle is moving in one dimension along x-axis only. So along x-axis only, this vehicle is moving. Actually, let me give you a little bit of theory. Now, when I started teaching, you guys also know that when you teach, you learn the most. So, in my PhD thesis, I did use the extended Kalman filter, the extended version of it, and also uncentered Kalman filter. But I should have learned the theory of this stochastic process, like stochastic differential equation, before this Kalman filter. Because we are engineers, we are not mathematicians, so that's why I directly went to, even my advisor did not say that you can go through the stochastic differential equation first. But this Kalman filter is actually coming after this stochastic differential equation. After you go through stochastic differential equation, then you study Kalman filter, then you understand more. But anyway, So this is more applied. Now you will know what's going on. Okay, this vehicle is moving along x-axis. So therefore, you know its position in meter. So position in meters, I'm just making it very simple, one dimension. So the position is in meter. The unit of this x position is meter. And the vehicle's velocity is dxt over dt. The state of the vehicle at any time, the state of the vehicle I denoted with q at time t. Q, make sure guys, in my note I did mention this vector with lowercase bold symbol. So, but when I write, I cannot write bold symbol. So that's why I put underline to make you notice that this is a vector, not a state. So this vector is called state of the vehicle. The state of the vehicle consists of position xt and velocity vt. Okay. Just to save some space, I did write it in the form of row vector, but do you know what it is? This notation? Row vector, and then here superscript you put t. Do you know what it is? So 1, 2, this is a vector. Okay. What about this 1, 2?
Oh, transpose.
Transpose. So this is transpose. So transpose means that row becomes column, column becomes row. So you have, to save some space, this column vector I denoted with the row vector and a transpose here. When xt and vt are the position and velocity of the vehicle respectively. The input of the vehicle ut is real valued force modeled by Newton's second law of motion. So now we model the vehicle. Mathematical model of this one-dimensional vehicle is as follows. So you take the time derivative of xt, then you get vt, and you take the time derivative of vt, you get the acceleration, and using Newton's second law of motion, so F equals ma, where a is the acceleration. Okay, x double dot becomes the acceleration, it becomes F over m. Okay, so F is the force, and it did denote F with ut, and m is the mass. So now you model this vehicle using this differential equation. So this is ordinary differential equation, guys. This is ODE, ordinary differential equation. This ordinary differential equation. Because we started with a simple vehicle, we are able to model it using ordinary differential equations. And in fact, guys, everything that you see follows some sort of dynamics. And this dynamics is modeled by differential equation. So this dynamics is modeled by differential equation. And there is a professor in Asia. He was actually telling a joke in class that he noticed that a guy was taken to hospital, and then 3 things that that guy needs to say when someone asks. One is his name. You should be able to tell his name, his father's name, and differential equation. So it's an Indian professor who actually joke of his students. So the point here is that this differential equation is so important that you simply cannot think anything without differential equation. Everything that you see around can be modeled using differential equation. Only thing is that you may not know the explicit expression of the differential equation, but some sort of dynamics is there. And human being is following certain differential equation. Okay? So everything can be modeled using differential equation. Only thing is that some systems, you know the mathematical model, you know the parameters, therefore you may represent the dynamics using differential equation, and some systems you may not. Your differential equation is unknown, but still differential equation is there. Okay, so now you have the ordinary differential equation that models this one-dimensional vehicle. What you do, you take these two differential equations and put it in the form of matrix. And this matrix form differential equation, we call this state space representation. We call this state space representation. So we have state space representation, or what you do, you combine these two elements, x dot and v dot, you put it as a column vector. So this column vector dimension, or this matrix dimension is 2 by 1. It's a column vector of dimension 2 by dimension 2. And then this is a matrix. This is a matrix. You call this a matrix, matrix of dimension 2 by 2, and this is a vector of dimension 2 by 1. Actually, vector of dimension 2, column vector of dimension 2, matrix of dimension 2 by 1, and this is a matrix of dimension 2 by 1, and this is a scalar. So this equation is called state equation. This equation is called state equation, and this equation is called output equation. This equation is called the output equation. This output equation, we write this output equation after we define the problem statement. Now, what is the problem that we are going to solve? The problem that we are going to solve here is that this vehicle is moving along one axis. The vehicle is moving along one axis. All what you know is that from its speedometer, you just know its velocity. You can measure its velocity, not its position. So you simply do not measure its position. You absolutely have no idea where it is, okay? The position. Only data that you have access to is its velocity. So velocity is known, but not the position. The problem here is that we want to estimate the vehicle's position as a function of time, and we want to estimate the velocity as well. Velocity, again, we get the noisy measurement, velocity measurement. We do not know the exact velocity, so we want to estimate the position and velocity. Now, after I go through all these steps, all the theory, Kalman filter theory, eventually you will see that the vehicle is able to estimate its position and velocity. So, for example, I just wrote a piece of MATLAB code here. So initially vehicle started with at position 2 and velocity 4, and you still do not know what is Q hat and Q hat plus. You do not know the covariance matrix, the state error covariance matrix. You do not know the positive noise. I will go through all of this, but I just want to show you the output, that how vehicle estimates its position and velocity. So vehicle started, as you can see from here, that this blow line is basically vehicle's ideal position and velocity, and this green is the estimated position and velocity. And then uncertainty associated with the estimation is given by this uncertainty array, which is actually coming from the covariance matrix that we will go through. So eventually, we are looking into this sort of result where we can estimate the vehicle's position and velocity based on the noisy speed measurements only. That is the problem statement. So given the noisy speed, how we estimate the vehicle's position and velocity. Clear? So that is the problem that we are solving. So now you see that this model, we call this state space model, has two different equations. One is the state equation, the other one is the output equation. Output equation, we just see the velocity. We just see the velocity, we just can measure the velocity. Now guys, can you see what is the okay, 0, 1. What is the dimension of this matrix, guys? 1 row and 2 columns. And what is the dimension of this vector? 2 rows, 1 column, 2 by 1. So now these two matrix multiplication, you can do matrix multiplication. This matrix multiplication is such. First row, first column. So this times this, 0 times x becomes 0, plus this times this, 1 times v becomes vt. So this becomes vt. So your output yt is basically the measurement. So this noisy measurement that you get right from here. That's why I put this as an output equation. We just get the noisy measurement v. So our problem is that the problem, I'm just going to, even though I have it written here, I'm just going to write right here. So given noisy speed measurements, estimate speed measurements of from 1D vehicle, estimate its position and velocity as functions of time. As functions of time. And all the parameters that you were given is that vehicles mass is m in kilograms, okay, and vehicles input is force in Newton. Okay. So these are the, like, you have certain force, you apply certain force, but this force is going to be noisy as well, okay? And you know vehicles mass in kilogram, again mass will have some noise as well. So all these parameters are noisy, okay? Then, and the measurement that you get, which is the vehicle's velocity, that measurement is also noisy. Now, how you estimate the vehicle's position and velocity? So that is the problem. And for this problem, we want to we want to implement this estimation problem using digital computer. Because we are estimating this problem using digital computer, we will need to discretize this continuous time system. And that's what Dr. Low is going through, discrete time signals and systems. So we start with this continuous time system, but because we will be implementing this algorithm using a digital computer, which means that onboard computer will process all the data and estimate, okay? So that's why this continuous time system will be converted into discrete time system as such. So what we are going to do, guys, yeah, please pay attention. So this is the critical part. So we have time starts from t equals, let's say 0. Because we denote it with initial time t naught, which is 0. And final time tf. And we discretize this time as such. Okay. How we discretize? So we say time instance, we denote time instance using variable k. Time instance using variable k equals 0, k equals 1, k equals 2, k equals 3, and so on. And this time, we call this sampling time t. Sampling time t, we sample time, and then this sampling time we denote it with t. Now, each time instant you can actually calculate the time here. So time at this point, the time at this point I denoted with tk. Tk equals k times t. So the time at this point is t sub k is k times t. Now you substitute k equals 2 and t, depending on the sampling time, let's say sampling time is 0.5 seconds. In that case, time tk at time instant k equals 2, the time is going to be 1 second. So this is 0.5, this is 0.5. Now when you implement, so that is another point where people make mistakes when plotting actually. These mistakes happen when, happens when you plot. So several mistakes can happen here. So you chose the sampling time, and because of the sampling time, because you are approximating using sampling time. If you make the sampling time huge, this estimation will not work. This estimation will simply not work. Okay. Now what you do? Let's say we have this sampling time small enough, and then you discretize the time as such. Okay, so let's say we have t equals 1 second, guys, just for the sake of simplicity. Sampling time t equals 1 second. So we have how many time intervals, guys? Here, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say this is another one, 10, and this is 11. There are 11 time instants. There are 8 time intervals. 11 time intervals, just for the sake of simplicity. There are 11 time intervals. Now, when you plot the vehicle's position, so you plot vehicle's position at this point, or plot vehicle's position and velocity at this point. You plot vehicle's position and velocity at this point. So, I need to explain this. So this is where people make mistake. So we have time vector for this example. Time vector you start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the time interval is going to be 11 here. So you have 1 here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Time interval is 11. Now, what is the dimension of this vector, guys?
Rows, 1 column?
No, it's 12 rows. It's 12 rows, 1 column. So that's where, when you plot, that's where people make mistake, when you discretize. Okay? So it started from 0 and you end with 11. So there are 12 rows and 1 column. So if you make it 11 rows, 1 column, you will see there is a dimension mismatch, and you will see it. Okay? So that's where people make a mistake. Now, you want to get the estimated position and velocity of the vehicle. So you will see, if you solve this ordinary differential equation, if you use simply the discrete time version of the equation, you will see at time t0, so this is t0, t1, t2, dotted, t11. So at time t0, you get x0, v0, x1, v1, x2, v2, and so on. Dotted, x11, v11. Okay? So this is going to be dimension of 12 by 2. You can actually extract them and make individual column vector. That is also okay. But you can actually, to save time or to minimize the number of variables used, you can use a matrix variable that can actually vary these two variables at once. So now let's move on to this equation. Look, this equation, it is simply a for loop. You start with vehicle's position at time 0 and vehicle's velocity at time 0. You substitute x0 here, v0 here, and the velocity v sub k, you start with velocity v sub k, you get the position at time instant k plus 1. And then you have vk plus 1 equals vk plus t qk and mk. So I'm going to explain a little more this equation, how this equation works. Okay. So yeah, after this explanation, I'm going to stop because this is quite complex. I need to go through this story, so I just don't want to take this. Okay, guys, can you give me the equation? Vehicle is moving in this direction. At time t equals 0. So this is, for the sake of simplicity, I'm just going to make sampling time t equals 1 second. Okay? So this is t1, this is t2, this is t3, and so on. So this sampling time is 1 second. Now, k equals 0 here, k equals 1 here, k equals 2 here, k equals 3 here, and so on. I assume that given vehicle's position and velocity at time t equals 0 is x0, V naught. So we assume that the vehicle's position and velocity is x naught and v naught. And let's say in the exam, I'm going to give you numerical examples, guys, numerical values. So in the exam, you simply don't write the equation. So yeah, you will be applying equation to come up with numerical values. So let's say x naught equals, start with 2 meters, and velocity at time 0, let's say 1 meters per second. Okay? So now, the equation that I have is xk plus 1 equals xk plus t times vk, and vk plus 1 equals vk plus t times uk over m. So this is the equation, discrete time equation. So we converted from vehicle's model using Newton's law from this equation to this discrete time equation as such. Okay, so now look. At time 0, I have 2 meters.